So in order to help alleviate the issue with conflict misses, we use what's called an associative cache, or sometimes we call it n-way set associative cache. But for short, we often call these just associative caches. And so in a set associative cache, we have multiple ways for each set. So it's like if you have a freeway that you're, or a highway that you're going down, instead of having just a single lane going in one direction, you know, stuck behind a slow car or something, it has two lanes, right? Two options. I can go in, you know, the right lane or the left lane. And so what we have here is, so we're going to use the same size. We still are storing 8 words. So our set, the number of sets has to go down. So here we have 0, 1, 2, 3. We have 4 sets now. Okay, so 2 to the 2. So we're going to use just 2 bits to indicate which set it's going to map to, the memory address is going to map to. And it could actually map to either of those ways. So let's say, for example, so this is the set number here. This is our set number. Say we had some address. What's this pointing to? It's pointing to address set 2 here. So let's go ahead and put that. So if we map to set 2, right, 1, 0 set bits, and let's say it's just that. So this would be address hex 8, right, all zeros, and then a 1, 0, 0, 0. So this is address hex 8, and it would map to this set. And if it's completely empty, it can choose which set to map to. But let's suppose one of them had already had some data, you know, some random tag in it. Data, that memory address, we'll just, you know, whatever, some random data that it had in it. And let's say, so 32 bits of data. And let's say that this way of the cache were not valid, then, you know, it wasn't a hit because, well, now we have to compare 2 tags and say, is this tag, you know, the same as the tag that I'm looking for? I would compare here, this would get a 0. And I would also compare on whether it's the same as this tag, but would also need a valid. In this case, this valid here would force hit 1 in way 1 to be 0. And because it wasn't a match in way 0, that way of the hit would be 0. And so we would pull data into this way, put 0 in the tag, whatever data is at memory address, whatever's at memory address 8 would go into that data in way 1. And so the next time we access memory address 8, it would be a hit. Right? Would see that data, and now let's erase all this. Now it would compare that tag to the tag in way 1, and it would say, yep, hit. We'd have to make sure to replace that valid with a 1, and now would get a hit in way 1. And this would say hit, yes. The processor would say, yes, it's a hit. And hits of 1 would be a 1. And so we choose from this multiplexer, we choose data from way 1. So again, set associative caches are simply called associative caches, alleviate some conflict misses. So here's an example of that, of what would have been that conflict miss. Hex 4, accessing address hex 4 and hex 24. Right, hex 4. And this is address hex 4, and this is address hex 24, or hex 2, 4. In our direct map caches, we use these 3 bits, these map to the same set, and it was a problem because there was only one way in that set. But now, if we use our 2-way, this case is a 2-way set associative, so it can be n ways. We could have 4 ways, for example, but this is a 2-way set associative. Again, we're just using 2 bits because of the, we only have 4 sets now for the set bits. these still map to the same set, but it's not a problem. So hex 4 is going to come in here and map to way 0, so address hex 4, and then on the next access to hex 24, there's another way available, assuming the cache was cold, and so we map to that new way. And we put the tag bits, of course, for each of those addresses in. And so the first time through is a compulsory miss. The first time through this loop is a compulsory miss. But now the next time, again, this is running 5 times. And so we have 5 times through this loop. And we have 2 accesses that are misses. So we have 2 misses. But the next 8 accesses, right, the next 4 times through the loop are hits. So we'll have 2 misses total and 5 times 2 or 10 memory accesses. And so this is 2 out of 10 is the miss rate, or in other words, 1/5 or 20%. So associativity reduces conflict misses. And here's the example of that. We can have fully associative caches. So a fully associative cache has basically the number of blocks is the number of ways. So in this case, we have a fully associative cache means there's only a single set, so we don't use any set bits. And this, for example, when we had our 8 blocks, this is now an 8-way, fully associative. There's only a single set, in this case, an 8-way associative cache. If we had 16 blocks to be fully associative, would have to have a 16-way associative cache. So fully associative caches reduce conflict misses, but they're expensive. So remember that now it could be in any of the ways, right? And so now we have to check the tags for each of them. We have to say, hey, when our address comes in from the processor, here's our address coming in. We don't have any set bits anymore, and so here are our 2 bits on the bottom for load word addresses. Those are always 0, but now the rest of it's a tag. And then we have to compare and say, hey, was that one? No, that one. Compare all of the ways of the cache. Now we have to do all of those comparisons to see which way. And then our multiplexer is also bigger now too. Now we have an 8-to-1 multiplexer to choose which of the ways that was in. The data we're looking for is in, or perhaps it's not in there. Remember, we could get a miss as well. So a fully associative cache is great with helping with conflict misses. Now we can map to any one of those 8 ways, but it's expensive.